Hi everybody, this is lecture 26 and today I want to tell you about electromagnetism. I want to tell you applications of the mathematics we've discussed so far in our course in this subject. So at the end of today's lecture, my goal is to explain to you some interesting things about this thing. This is the charger that came with my iPad. One of the things it does is it converts 110 volts of input into 5.2 volts of output, and so this it converts the power that the power company supplies my wall socket with into something my device can work with. So this is something I'd like to explain to you today, and the point being at all times to illustrate the main theorems that we just learned about, the Stokes' theorem and the divergence theorem. We'll also talk about beside this, there's another application, but I'll get to that in a second. All right, so engineering and physics through mathematics, that's the theme for today. So we're talking about electromagnetism. Before we discuss engineering and physics, I first should tell you a few things, a little bit about electromagnetism. Thankfully, everything there is to know, in a certain sense, everything there is to know about electromagnetism just fits in this panel right here. So let me give you that summary. Let me write those equations here that tell me everything, tell us everything there is to know about electromagnetism. So first, what are we talking about? Well, we're talking about interactions between certain objects in the world that we call charged, right? Physicists and people have identified that certain objects interact with other objects in a special way, but only if both of them are charged, right? And the degree, and different objects can be charged to different degrees, and so we associate with each object a number that we call its charge, and that measures how strongly it interacts with other charged objects. Okay, so there are charged objects and they interact, right? They exert forces upon each other. And if I have a collection of charged objects, if I have a collection of charged objects on each of them, I get a resulting electromagnetic force. And the difficulty is knowing what is the force on each of the objects. So this is the best way to understand this force is to think that it's generated by two vector fields, two auxiliary vector fields. They mediate between the charged objects and the forces that they generate. And these auxiliary vector fields are called the electric field, that's usually denoted by E, and the magnetic field, that's called B. And the rule is that the force on a charged object is equal to its charge times E plus the cross product of the velocity of the object with the magnetic field at the position of the object. All right, so Maxwell's equations tell us what the electric field and the magnetic field are given the positions of all the particles in the world and the velocities of all the particles in the world. Right, so here are Maxwell's equations. It's just 4 equations. They tell us they involve the divergence and the curl of the electric field and the magnetic field. They don't give us E and B directly. They give us the divergence and curl of the V and B, and then it's our job to extract from these equations what E and B are. And so here are the equations. So the first one, the divergence of the electric field is the charge density divided by a constant usually called epsilon 0. So that's the first equation. The second of Maxwell's equation tells us that the curl of the electric field is minus dB dt minus the rate of change with time, minus a time rate of change of the magnetic field. The third of Maxwell's equations tells us that the divergence of the magnetic field is always 0. So this is because there are no magnetic charges in the world. There are only electric charges. And the fourth of Maxwell's equations tells us that the curl of the magnetic field is minus dE dt. So minus the rate of change of E with time plus the current density. So this is like charge density, but you take into speed, their speed into consideration, divided by epsilon 0. So today I want to give you applications of the first of these equations, right? I want to, let's just see. So let's see a problem here. I told you that all there is to know about electromagnetism is contained in these equations, but but it's not clear. I mean, it still takes some skill. It still takes considerable skill to be able to extract useful information from the equations in each case. So I want to show you how that's done. Okay, so my game plan is to extract from the first equation Coulomb's inverse square law. That's just something that's more straightforward to apply, and only it doesn't involve div anymore. It just involves addition, multiplication, division. It's an easy formula for the force between two-point charges. So I want to give you Coulomb's inverse square law, and I want then to use the second equation to show you how the second equation can explain the workings of a transformer. So first, let's get Coulomb's inverse square law from the first equation. To do that, let me just convert this first equation to integral form using the divergence theorem. So what we get is Gauss's law. Okay, so in Gauss's law, we draw up a closed surface S. So Gauss's law applies to a closed surface S. That's it's an ideal surface. It's an imaginary surface that you can place with your mind in space. So it's a closed surface in space, but it's an imaginary thing. What Gauss's law says is that if you place an imaginary surface in space, and then you ask what's the flux of E across this surface. So what's the flux of the electric field across this surface? Here, the surface being closed, I can indicate that the surface is closed by putting a circle in the integral sign. So Gauss's law is concerned with the flux of E across a closed surface, and what it says is, well, let's see. So let's derive Gauss's law from the first of these equations. So first, I'm going to use the divergence theorem. To conclude that this flux through this closed surface is equal to the triple integral on the region inside, I'll call it V, of the divergence of E times dV, right? This is a mathematical statement. And now let's so now we're in position to use the first equation. The first of Maxwell's equations tells us that the divergence of E is the charge density divided by epsilon 0. Okay, so epsilon 0 comes out of the integral. And then I'm left with the triple integral of the charge density. This tells us that the triple integral of the density is just the total charge inside the surface. Right, so the flux, so the first of Maxwell's equations gives us Gauss's law, which tells us that the electric flux is equal through a closed surface is equal to 1 over epsilon 0, that constant, times the charge inside. So it's proportional. The flux is proportional to the charge inside. Okay, so this is Gauss's law. Let's now use this law to get Coulomb's inverse square law, which is something we can apply in this straightforward situation. So here I have a large charge, big Q, and I want to know what's the force that big Q exerts on a test charge, little q. R is the position vector, is the vector that points from big Q to little q. I can imagine that that big Q is located at the origin of space. All right. So the force. So here we're in the we're going to assume that neither of these charges are moving, and that these are the only two charges in the world. And so the force by the, oh god, I keep forgetting it. By the Lorentz, so the Lorentz force is Q times the electric field. There is no V, nothing is moving, so there is no V term. So the magnetic field doesn't enter. So the question is, what is the electric field at, what is the electric field generated at the position of Q by capital, at the position of little q by the big charge capital Q? And what we're getting towards is that it's going to be a multiple this number of the unit vector that points from big Q to little q. Right, so the force is going to live on this axis, and it's going to, in its magnitude, we're going to see is going to drop off with the square of the distance between the two charges. So if the charges go, or if you move them to be twice as far than the electric field, and therefore the force will be just a quarter as strong. So our job is to understand why this drops off. With what's the formula for E for this scaling factor in front of the direction. I should note that the direction of the direction of the force must necessarily be the force must necessarily point either away from, so the force at little q must either point away from big Q or toward big Q, because the problem is symmetric around the axis that joins the two charges. And also that the magnitude, this factor in front of the direction, this magnitude can only depend on the distance between the charges, right? If I rotate, just tilt my head and look at the problem like this, then physically the problem is the same. The observer shouldn't change the physics. So the electric, the magnitude of the electric field, that's an observable, so it shouldn't depend on the observer. Okay, so the point is that this expression for the electric field comes from symmetry. And we wish to understand, using Maxwell's equations, what is this factor here up front. So I'm going to use the integral form of the first equation that I derived just a moment ago. So I'm going to draw, the trick here is I'm going to draw a surface I'm going to consider a smart surface around big Q, right? The sphere around big Q, which has little q on its boundary. The sphere centered at big Q, which has little q as its boundary. And then the charge inside that sphere is Q. So let's use Gauss's law, right, which came from the first of Maxwell's equation. It says that the charge inside that sphere divided by epsilon 0 is equal to the electric flux. So Q over epsilon 0, that's the charge inside the sphere divided by epsilon 0, is equal to the electric flux. That's the double integral over S of E times ds. Okay, now let's do some math. Let's work out, so first let's remember that ds is the unit normal times ds without the arrow, the area element on the surface. Let's also note that on this surface, the unit normal is just it's just the vector r, but placed at points of the surface. So that's r divided by its length. Right, in here I'm imagining that the point Q could be anywhere. So I'm viewing r as a function of points on the sphere. So n is r dot r. And so when I combine these two things, if I do E dot n, here I do the dot product, I get the length of a unit vector squared. That's 1 times, so the double integral over S of this scalar times ds. Okay, I don't know why I turned green there, but the point is that on a sphere, the distance from the origin is constant, so I can pull this out, and then I get that E. I can pull E out, so I get this multiplied by the integral of ds on the sphere. That's the area of the sphere. That's 4 pi times the radius squared, which is this distance here squared, times r squared. So the conclusion, our conclusion here is that E of r, so therefore E of r, the magnitude of the magnitude of the electric field, well, it's not really the magnitude, there's this number in front of the direction here. The scalar form of the electric field is, if we put this together, is going to be, so there's a 4 pi, so I just divide, just bring this to the other side, right? So I just get 1 over 4 pi epsilon 0 times q over the distance from the origin squared, the distance from the source charge squared. Right, so if I want to know the electric field generated by a charge at the origin, it's just 1 divided by 4 pi epsilon 0 times the charge divided by the distance from the origin squared. Right, this electric field drops off with the square of the distance, and the force, if I put another test charge little q there, the force is going to be little q times this number. So you end up just multiplying, just doing high school arithmetic, you end up multiplying the charges and dividing by the square of their distance. It's a pretty straightforward thing. So this is a good example of how we use the divergence theorem, how we use mathematics of this class to go from these synthetic laws to something that you can apply in a specific case. Okay. So this is amazing. It tells us how, it shows us that the electric force behaves in some situations just like gravity. And if we have an intuition for gravity, then we can bring over that intuition to electromagnetism. It gives us understanding. All right. So let's move on to the engineering application that I promised to you at the beginning of the lecture. So we're looking again at something like this, as I said. So if we read it here at the bottom, it says converts 110 volts. So 110 come in and 5 volts come out. So this is our transformer. So I drew a schematic for you. It's a black box that does this, right? The 2 wires come in, and you can see the two wires are basically at the wall, and they connect over here. And then there is another 2 wires that come out of blue, but they're here wrapped together in this. It looks like there is only one, but there is in fact 2 here hidden from your side, from us. So we're talking about voltage. I should of course tell you what voltage is. So before I discuss transformers in any detail, let's just see what voltage is. So voltage, the voltage on between two ends of a wire is this. So let's say, let me draw that. Let's say I have a wire over here, right? So the voltage V between the two ends of the wire is just the integral over the wire, so I'll call it C, of the electric field dot dr. Right, so this is, so instead of doing, so if we were integrating force along a curve, we would get work done by that force along a curve. The electric field is not really force, it's force per unit charge. It has units of force per unit charge. So here we get work per unit charge. So voltage is the work necessary per unit charge to move a unit charge along this curve. So if this voltage is positive, then it takes a positive amount of work. It takes some forces acting on a particle to move it from the one end of the wire to the other. On the other hand, if the voltage is negative, then a positive charge will have a tendency to move towards, along this wire in the given direction. But if I have a negative charge, then it's the other way around. If the voltage is positive, then the charge wants to move along the wire and by itself, without you having to exert a force. So this is the thing we're discussing. A transformer is this box that converts voltages, and voltages are defined like this. Now let's look a little in detail into this box. So if you pick this thing up in your hand, you'll see that it's kind of heavy, and the reason is that it has iron inside it, ferrite, some sort of iron-like metal. Here's the schematic. So it looks like this. This is not the schematic for the transformer that's inside Apple's charger. But it's a similar one to that. So the box. This is detailing something you could put inside this box to do this transformation, right? So here's what we have. We have an iron core, a piece of metal, and it's heavy, right here. And then the red wire, it's the two red wires, they're actually connected inside, right? They do this. And the blue wire, on the other hand, does the same thing, but on the other arm, on the other side of this ring, of this square. What's transforming? So you see the red wire and the blue wires never touch. The voltage of the red wire is transformed into the voltage of the second wire via the magnetic field. So what carries the voltage from here to here is a magnetic field, and the role of the iron core is to constrain the magnetic field confine the magnetic field within it. So we use the iron core to guide the magnetic field where we want it to go. So this is an important feature of this design is that the number of turns that the number of times I wind the red wire is wound around the core, around the iron, is different from the number of turns that the blue wire is wound around the core, right? The relationship. So if I want 110 volts to be converted to 5.2 volts, I need a very specific relationship to hold between NP, the number of turns for the red wire, and NS, the number of turns for the secondary wire. Right. So what I want to tell you in the last minute of today's lecture is how much bigger, and if I want to go from 110 to 5.2, NP has to be bigger. So at the end of today's lecture, I'll tell you how much bigger NP must be than NS. So it's going to be a number like 10 times or 20 times or 30 times. So let's work that out together. Before we examine this picture in more detail, let me just say a few words and show you a few pictures about what's going on inside Apple's charger. So here are a few pictures that I took from the website you can see below, and so this is Apple's charger opened up, and you can see, so the transformer is this yellow piece over here, right? It's a pretty complicated thing with a bunch of components, and we're interested in the yellow part. That's the transformer. It's called a flyback transformer. Not exactly the same kind as in this schematic over here, but it still shares many of the same many features with the one we're going to discuss in more detail. I should note that this little box is pretty complicated. Has a bunch of components, not just a transformer. Here's the circuitry underneath it. We're just talking about one piece of it. So we really have no right to be ever bored in life. There is so much that we can learn, so much interesting things in the world for us to learn about. So let's look at that. Let's look at that this yellow piece over here, the transformer. So more pictures from the website. So the first thing is what happens if you take the tape. So the whole thing is wrapped in so if you look here, the whole thing is wrapped. The whole transformer is wrapped in insulating tape. If you wrap the tape off, if you take it off, then you find something like this. So there is an iron core. So there's a piece of iron here, and then there is more tape. If you wrap that off, you see a bunch of copper wire that goes around it. And if you take that wire off again, and then take more tape off, right? Take the tape that's underneath here, you'll find the secondary wire, right? First we had the primary coil, and now we have the secondary coil, just like in the picture, in the schematic I drew before. There's a primary coil with a large number of turns. There's a secondary coil, secondary winding with a smaller number of turns, and there's iron that they wrap around. So here they were both wrapping around a single piece of iron rather than the two arms here on the side, but it's a similar thing. So this wire looks thicker because it's insulated. Next up, if we continue, just with our hands fiddling with this, if we unwind if we unwind the inner winding, so if we take this, this is the blue wire. If we take it off, we're left with more tape. Take off the insulating tape, and you're left with a little bit more of the original. So the second half of the original of the red wire from before. This is just to say that what I'm taught. This is to indicate, to bring to life the discussion. These pictures from Apple's charger just are remarkably similar to the simplified model I'm discussing with you now. So let's look at that model. We want to understand the relationship between NP and NS. Our working horse for that is going to be Faraday's law of induction. This comes from the second of Maxwell's equations in the order that I wrote them for you a moment ago. So the voltage. Here's Faraday's law. So we have a wire, and we're measuring it's almost a closed wire, but we're measuring the voltage at the two ends of the wire at the end. The voltage at the two ends, just before they meet, is, well, by definition of voltage, it's the integral of the electric field with respect to dr, right? And this I can compute. So this wire is nearly closed. I'll just say it's closed, all right? And and then I can compute this integral by using Stokes' theorem. So here I'm going to use Stokes' theorem. And what I get is the double integral along the surface bound, so I'll just call this S, the surface bound by this wire of the curl of the electric field with respect to ds, right? The flux of the curl is, so if I have a surface and I integrate the curl of an electric field by Stokes' theorem, I can forget about the curl and remove one of the integrals, just replace the surface by its boundary curve and get this integral over here. Okay, so by Stokes' theorem, the voltage is the flux of the curl of E. Now, using the second of Maxwell's equations that I wrote before, let me remind myself what that equation was. It said that the curl of E is minus dB dt. So if I integrate minus dB dt, I get V. Okay, so here's what I'm going to do. I'm going to assume that this surface is not changing with time. The wire is sitting still. Then I can bring out the derivative and the minus sign. And then I'm left with the double integral over the surface of the magnetic field with respect to ds. So this thing is the magnetic flux through this surface S. So the voltage around a closed loop is equal to minus the rate of change of the magnetic flux through the surface bound by that loop, right? So this was, we were originally interested in electric field and voltage, but we got wound up with the magnetic field in the process. And that's fine. So here is the magnetic field. We can definitely work with it too. So if this magnetic field is not changing, if none of the charges are ever moving, or if their speeds are always constant, then this magnetic field is not changing and this voltage would be zero. But if they are changing in the electric dynamic situation, then I could have a voltage at the around this closed loop. So that's what Faraday's law is telling us. Okay, so now equipped with Faraday's law, let's understand the relationship between NP and NS. So I'm going to so we want to relate VP, the voltage on the red wire, with VS, the voltage on the blue wire, at the end of the two ends of the blue wire. So let's see. So we want to understand flux through the red wire and flux through the blue wire. I'm going to state that, relate both of those with the flux through the electric flux going around this iron core. So here, let's look at a little section of the iron core. Right, this is area A, cross section area A. And let's look at the magnetic field, which goes along with the iron. That's why we chose to work with iron to begin with. So the magnetic field looks like this, and it's perpendicular to the cross section of the iron core. And so the magnetic flux through this area S, so the flux through S is phi, which is equal to just the area S times the magnitude of the magnetic field. Right, and the point is that this could be changing with time. This, in fact, changes with time. For this sort of transformer, this changes with time. So this transformer is for alternating currents. So the voltages are fixed, but the currents are changing their sign very, very, very often. And this change creates a change in the magnetic field. and therefore on this product. So this phi, the point is that phi changes with time, and that's the flux through this cross section. Now let's look at our primary, at the voltage Vp, the primary voltage. That's going back to the formula in the previous slide. That's minus dB dt. Sorry, minus d dt of the flux. So the flux through this, if you look at the flux through the surface bound by this red wire, really all that the contribution is here. The magnetic field is confined within the iron core, so there is no flux on here. There is only flux coming from this part. And you should imagine that this closes, this circuit closes somewhere on the left of the picture. So the flux through the red wire is the number of turns is Np times the flux through a single cross section. And similarly, the voltage on the secondary wire is minus ddt of the number of turns in the secondary wire times the flux through the cross section, because this gives me the flux, the magnetic flux through the blue wire. So the conclusion that we're working towards is that, Vp over Np. So if I divide Vp by Np, so Np is a number, right? I can take it out of the derivative. That's the same as the voltage in the secondary wire divided by the number of turns in the secondary wire. So now going back to the example of Apple's charger. So if the voltage in the primary winding is 110 volts and the voltage in the secondary winding is 5.2 volts, then we want that the number of turns in the primary wire is 110 over 5.2 times the number of turns in the secondary wire. That's approximately, so if we do the division, 21.15 times NP. Let me just say that this thing here we're multiplying is approximately 21 times 0.15. So you see that if I want to convert 110 volts into 5.2 volts, I can use I can build a black box like this, where just winding the red wire 21.15 more times than I do the blue wire. All right. So I hope this lecture exemplifies how we can use the theorems in vector calculus in real world situations, and serves as a good complement to our previous discussion of applications, which were to fluid mechanics. So with this, we've now touched in this class a wide range of topics and discussed them comprehensively, even so how they're used, what they're good for, and so on. Touched on the main applications. So with having done that, I want to thank you for listening, and I'll see you guys for one more time next time. Okay, bye-bye.